of reinforcement learning and optimization, bring some new techniques into the space from optimization. So I'm excited to hear about recent work.
Okay, so it's my pleasure to be here, and so I'm going to talk about reinforcement learning, complexity theory, and especially how to reduce the complexity using feature space. Okay, and some of you might have heard this talk before. Okay, so basically our motivation is to understand why reinforcement learning could be so successful empirically while we have little theoretical guarantee about it. So if you look at all the empirical successes of RL, we can pretty easily see that well, in computer games or in like Majorco in robotics that can be simulated. Apparently, as long as we have, I would say, enough, for example, credit for cloud computing, then we can always get something that looks reasonable with a good, maybe human level performance or superhuman level performance. But however, if you look at all these applications, especially those computer game applications, so one thing in common about this is usually the game or the robotic system can be fully simulated, which basically means that the reinforcement learning algorithm has access to infinite amount of data. So then the problem sort of becomes or more computational rather than statistical. Okay, but however, so we haven't really seen much RL in applications where data is limited. So one example is, can we use reinforcement learning to optimize clinical pathways, to optimize clinical treatments? So I can claim yes, but I think all the medical doctors, they will not agree. Okay, so for one particular clinical condition, the data people have is usually very limited, and it's difficult to model and also difficult to figure out what's the right way to figure out what are the compounding factors, hidden factors, and whether the model is reasonable or not. And this is further true in scientific study. For example, if I want to understand how a single cell evolves from a healthy state to a cancer state, and then all the data we have could be obtained from wet lab experiments. And then data are going to be super costly and take a long time to collect. And also further, like in clinical trials, if you try to understand the advantage of one policy against the other one, usually one data point could be one human being. And so data are very costly, and we cannot really be as, I would say, we don't really have abundant data as in the computer games because we really want to make use of each data point in the best way. Okay, so a very basic theoretical question would be like, for example, I want to estimate a 90% optimal policy, or maybe just 50%, or 99%, depending on the nature of the problem. Then how many data points do we need? And a related problem is, okay, so now we want to learn to control in a purely online fashion. Then how much regret do we have to pay? And how much regret is needed at minimum? So to answer these questions, so let's just look at, let's review the very basic terminology for Markov decision process, which is the simplest non-structured model for stochastic control. Okay, so let's say that we have a Markov decision process, which is a random walk over S states. And every single state of the random walk, we have a number of actions from the action set A to choose from. And at every state, and given an action, there's a reward. So the reward is a function of state and actions. And the reward could be stochastic as well. And then the system transitions according to some probability law, which we denote by P. So this is a purely OR problem if we know everything about the rewards and the transition probability. And this becomes an optimization problem, which also has a very nice linear programming formulation. And we know, like Yin showed that policy tuition is actually the best algorithm with strong polynomial guarantee. So if we know everything about the model, then the problem is basically pretty well understood. And also, usually we call this tabular MDP to mean that we have little structure knowledge. So I don't have any structure knowledge except for that I know that I have a transition probability matrix, and it can be any transition probability matrix. Okay. So in this basic case, let's consider sample complexity. So by one sample, we mean a triplet of state, action, state, transition. So this triplet is one single sample. Okay, so So one basic question is, so what is the sample complexity for learning an absolute optimal policy? So let's look at a very basic setting with a generative model. So I believe generative model is proposed by Shum in his PhD thesis. So it means that, okay, I have a system which can be fully simulated, and we are allowed to specify a state and action for the system to begin at. And the system is going to generate one single transition. So I don't have to know the transition probability model, but the generative model should provide information about the unknown transition probabilities. Okay, so in this case, so the first complexity question one typically asks is, what is the lower bound? So what is the benchmark? So the benchmark is proved by Azar and a bunch of folks at DeepMind. So they show that, okay, the minimal sample complexity needed for finding a good policy scales linearly with S, number of states, A, number of actions, and the third power of 1 minus gamma. So gamma is the discount factor. So 1 over 1 minus gamma is like the temporal horizon of the process. Okay. And so we try to figure out if we can actually achieve this lower bound. So actually, the answer is yes. So a plain vanilla Q-learning algorithm or empirical value iteration is actually going to work pretty badly. But if we do a bunch of things like variance reduction and also to leverage mathematical structures of the Markov chain, then one can actually construct an algorithm to be statistically optimal. So I'm not going to show you the algorithm, but I just want to show you that this algorithm achieves the upper bound, which is here. And also recently, I think Agawa, Yang, and Shum, they show that actually in certain scenarios, it's possible to achieve minimax optimal complexity using a much simpler algorithm. Okay. So this is what we know about tabular MDP. Okay. And so when we work on the tabular case algorithm, so we got the questions that, okay, so why do you work on a tabular problem? I mean, it's basically the tabular MDP is not a good model because the number of states is typically too big to be meaningful in any practical applications. Okay, so suppose that we are working with a state space of dimension D. Okay, so and then say that I don't have any structural knowledge. So to make things computable, we have to just do a vanilla discretization of the state space. And if we do so, then I'm going to get basically exponential in D number of states after vanilla discretization. Okay, and now if we look at the size of the policy space, it's going to be number of actions to the power of number of states. And even if we take logarithm of the size of policy space, it's still going to be exponential in the dimension of state space. So basically, I'm trying to say that, okay, so the tabular case results are nice theoretically, but in practice, S is just too big to make anything meaningful. Okay, so now, so we propose that, okay, let's try to think about dimension reduction. So let's go back to the Bellman equation. So the Bellman equation is the optimality principle for stochastic control. So let's see what can we learn from there. So here in the slide, I'm writing down the Bellman equation for infinite horizon undiscounted MDP, just because it's simpler mathematically. Okay, so this is basically a set of nonlinear equations, and we have basically S nonlinear equations. Or if we think about a continuous state problem, it's really just a continuous infinite dimensional continuous variational inequality. Okay, so basically for every single state, we have to make the right decision. We have to find the right A to maximize the right-hand term. So I have one max operation for every single state. So I have nonlinearity and high dimensionality together, and they're coupled. So the problem becomes hard. So we propose that, okay, what if we return to the linear programming formulation? So it's well known that Bellman equation is equivalent to a linear program in the value function space. And if we play with the linear program formulation, it actually has an equivalent saddle point formulation. And so the saddle point formulation is very interesting. So we have a minimax problem, and its optimal saddle point is equivalent to the solution of Bellman equation. And the primal space is the space of all value functions. And the dual space is the space of all state action distributions. And if we reach the saddle point, then the optimal primal undo variables will happen to be the optimal value function and the corresponding state action distribution under the optimal policy. Okay, so in this way, actually, we have a very nice and clean duality between value function and, I would say, the ergodic measure under the optimal policy. So now this is, again, a huge primal dual optimization problem. It's S times A for the primal space times S for the dual space. Okay, but however, now because we have linearity, we can try to reduce its dimension. So now let's think about a common approach for reducing dimensionality in RL. So what if we have a state feature map, so which is actually a common practice for solving computer games in real world. Suppose that I have a feature map that maps every single state to a vector, a finite dimensional vector. Okay, so for example, like I think even 20 years ago, Tetris, which is the simplest game ever, Tetris can already be solved using 22 features. And the features could be basically picked by practitioners, like the height of the maximum height of the wall, and with some profiles of the top level, profiles of the second level, and things like that. Okay. So what does it mean to use state features? So basically it means that one, we need to evaluate the value function of a state, which by definition involves a complicated sum over future trajectories. Okay. And instead of trying to compute the entire high-dimensional value function, one can try to say that, okay, I'm going to basically regress the high-dimensional value function against my feature space. So I'm going to reparameterize the value function using a weighted combination of features. And then basically, I only need to estimate a few of the weights, W1, W2, to recover the entire value function. So this is actually a common practice for Monte Carlo tree search and dynamic programming with rollout. So for example, when we do tree search, and at some point we want to stop growing the tree, and we are going to use this linear value approximation as a proxy, and then we can roll back to compute the policy. So this is pretty commonly used. And apparently this has limitations, which we'll talk about later. Okay, so suppose that we just want to approximate value functions in a linear space. Okay, so now what does it mean in the Bellman equation? So we have already shown that the Bellman equation, which is nonlinear, actually is equivalent to a minimax problem, which is linear. Very nice. Okay. And so now if we look at that, it actually reminds us of how do we solve parametric estimation and regression. Really, we are trying to approximate functions in a linear space. Then one simple thing we can do is, if I do have nice state features and action features to begin with, then we can restrict the constraint into space spanned by the feature functions. And then basically we can reduce the high dimensional saddle point in the function space into smaller dimensional saddle point problems, which can now be computed. Okay. So this is actually joint work with Li Hong, and in the audience, and also my student Yishen Chen. Okay, so let's say that we are happy with the state and action features, and we have already reduced the dimension of the Bellman equation. So now it's actually a moderately dimensioned saddle point problem. And still, we are in the learning setting, so we do not know all the transition probability matrices P. Okay, but however, we do have a simulator. We have the geometry model. So every time I have one single sample, basically I sort of have some noisy information about the Lagrangian function. So we can develop a stochastic primal dual gradient algorithm. So it's actually a primal dual policy gradient. So every time we have a new sample, which is a triplet, so the sample should tell me something about that unknown big matrix P. So we can compute actually unbiased partial gradients. And we are going to do a primal update and a dual update. And the dual update is actually in the space of ergodic state action distributions. So we are going to use Kullback-Leibler divergence as the Bregman divergence. Okay, so the actual algorithm looks like this, which is, I would say, pretty compact in my mind. So what's nice about this is now all the updates are in the low-dimensional parameter space. Okay, and one can always prove something. So for example, assuming that all the features are perfect to realize the actual high-dimensional functions, and then one can find an absolute optimal policy using sample size that is linear with respect to the number of, I would say, the dimension of state features and action features. Okay, and there are some additional dependence on some ergodic ratio and mixing time properties, which I'm not showing here. Okay, and we can also prove approximation guarantee when the features are not perfect. So I think the interesting message here is that it is possible to reduce the dimensionality of Bellman equations through the saddle point formulation, and the sample complexity is going to depend only on the dimension of the feature space and has nothing to do with the dimension of the original state space. Okay, so that's for sample complexity. Oops. Okay, so now another question is, okay, how can we learn on the fly? So what if we don't have a generative model? So a generative model is nice in a way that it is basically a simulator, so we can play with it in any way we want. But however, the sample optimal algorithms I just explained to you actually relies on the generative model to draw basically the same number of samples per each state or per each, I would say, representative direction of the feature space. However, in practice, we might not really have a generative model for us to uniformly sample the space we want. So let's think about just learning on the fly. So let's think about an H horizon problem. So we have to start with a fixed state. And the algorithm can only play the game from the beginning till the end of the H horizon. And whatever the algorithm observes is what can be observed. Okay, it has to act in the real time and make observations in the real time and then also update in the real time. And it's not possible to visit all states frequently just by nature of the problem. Okay, so we are not imposing any assumption on exploration. Okay, and we care about, sorry for having the Greek letters floating around. I have some formatting issue. Yeah. Okay, so we care about the regret. And the regret means that the cumulative regret of the incurred by the learning algorithm. So for every episode, we compute the difference between the highest possible score and the actual cumulative rewards earned by the algorithm. Okay, so that's the notion of regret. So basically, what might make things difficult is like one single action at the very beginning might basically jeopardize the entire horizon, the entire episode. And also, all the data are generated from the same game along the same trajectory, so there's a lot of dependency. So it's much more complicated than just bandit type of problems. And there were many existing works like the LQR work by Yassin and Chaba, and Van Roy has actually done very good work in terms of model-based RL with general model class. Okay. And also, Jin Chi and a few others, they figure out how to do Q-learning in a tabular case. And actually, there are many more works which I don't have space to cite here. And understanding the regret for RL, especially in the tabular case, has been studied for a really long time. Okay, so now we want to do it in the feature space. So again, I'm going to work with state action features. So I'm going to map a pair of state action into a vector. So if I have state feature and action feature separately, I'm just going to take their product. Okay, so I'm going to take a product, so I have a matrix, and then I vectorize it. And also I need a state-only feature. I call it psi. Okay, and also I'm going to make assumption that the unknown transition kernel can be actually fully embedded in the feature space. So this could be a bold assumption. So this basically means that the transition matrix or kernel admits a decomposition form, and I have a transition core matrix M star, which we do not know. Somehow we can view that the features sort of define a grid, and we are sort of like understanding the potentially infinite dimensional transition kernel from our grid. and then it reduces to a matrix, which is a transition core, the M matrix. Okay, so one may question, okay, why do we assume strong assumptions on the transition kernel? So it turns out that one can actually show that as long as we want to use linear models and features to parameterize the value functions, so to make sure that the Bellman error is always 0 in Bellman updates, so the transition kernel actually has to have such a decomposition. So somehow having such a decomposition for the transition kernel is roughly equivalent for using features to present value functions. So both of them have to be making sense at the same time. Okay. And the next, okay, so now let's try to do RL. So suppose that we're at the beginning of the N+1 episode, that we have already collected a bunch of trajectories so far. So the trajectories consist of like basically consecutive sample transitions, state action state triplets. So for each triplet, I'm going to map it into features phi and psi. Okay, so now I have 2 vectors for each transition triplet. And then we can do something very simple. We can just try to estimate the core transition matrix by matrix regression. Okay. So, but we do know that if we just estimate the model greedily using data, apparently, this is going to lead to very poor exploration. So we are going to borrow ideas from Linear Bandit to help exploration. Okay. So the idea is very simple. So since we simply want to estimate the transition core, and we want to estimate transition core from dependent data, so one can construct a confidence set around the empirical estimates. And the confidence set can be basically characterized using the empirical sample covariance matrix and some confidence bound. And then whenever we try to resolve the MDP, we're going to compute Q functions in an optimistic way. So basically, every time we do Q updates, we're going to consider the most optimistic transition core from the confidence set. Okay? And in this way, we can make sure that, okay, every time we are being optimistic and we are going to assign bonus to state actions that are more uncertain based on the data we have seen so far. And then in the new episode, we simply use the Q functions to choose actions greedily. So in this way, we can encourage exploration, and hopefully we can visit state action pairs with higher uncertainty more often. Okay. So one can prove some regret. And under a bunch of conditions, the regret for this learning algorithm is basically linear with respect to the dimension of the state action features. And also square root of d. So both of them are optimal. And the regret is independent of the original state space. However, the current regret is quadratic in H, which is definitely not optimal. Okay, but at least this regret is pretty polynomial with respect to the problem parameters, and it's a tractable algorithm. Okay, and instead of using explicit state action features, one can also use kernel maps. So now suppose that I don't have the feature map, but I have an Hilbert space with a known kernel function over the state action space. And then we can basically make the same algorithm work. And in this case, the assumption sort of translates into that the transition kernel, which we do not know, belongs to the product Hilbert space spanned by the unknown features. So the algorithm I described has an equivalent kernelization, and again, in this case, the regret depends on the Hilbert space norm of the transition kernel and a notion of effective dimension. Okay. So far, basically, we have seen that if we believe in the linear models and if the features are good, then it's possible to get sample complexity that depends linearly on the feature dimension. And also it's possible to get regret that depends linearly on the feature dimension. So these are nice results. And, but however, using features for RL has a lot of problems. So the one nice thing is if we want to do theory, then the nice algebraic structures make it possible to prove very strong zero guarantees. And also, actually, if we look at the feature representation, the algorithms, and the analysis, actually all the analysis has very deep connection to just regression. Okay, and there are not too many parameters to tune, which is also nice. But however, one assumption which was implicit in all the previous analysis was that the features have to be actually the good features. They actually have to span the right column space of the transition matrix. Okay, and if the features are not good, then there are going to be a lot of pathological problems. For example, it was pointed out in very early literatures on stochastic control that if the features were not perfect, a little bit of mismatch in the feature space might lead to oscillation in policy iteration, right? Because the iteration will just not converge. Every time I try to improve, I might be taken to the other side of the feature space, but simply because the feature space does not capture the full space of policies. Okay, and also there could be chattering, and of course, linear models are not as rich as nonlinear models. Okay, so now the question is, okay, the harder question is, can we just still do well without knowing the features? We know that if we know the features, then there's always something we can do, and also there's something to prove. But can we learn the features from the scratch? Okay. So again, so now let's think about a harder problem. So I won't be able to give you a full answer, but hopefully we can start thinking about this direction. So what should be good features? So for example, if we look at the definitional value function in the undiscounted case, the value function essentially is the limit of sums involving powers of the transition matrix or transition or multi-step transition kernel. Okay, so now if the transition, or say transition matrix, say the transition matrix P somehow does admit a decomposition involving phi and psi. So if that is true, then it's very easy to check that the value function has to lie in the space spanned by phi. And correspondingly, the invariant measure has to lie in the space spanned by psi. And also, so basically, the good features should come from the transition probability matrix, which we do not know. And all the previous assumptions basically assume that we know the feature phi to span the unknown transition matrix P. Okay. Okay. So next, so it will be interesting if we can simply learn features automatically from data. So let's make things simpler because this is a harder unsupervised learning problem. So I dropped the decision and action part. So let's just look at stationary Markov chains. Okay. So say that I have a time series x1, x2 to xt, and each x could be a vector. Okay. And say that we believe that the time series we observe is generated by a simpler underlying physical system. So somehow the unknown transition probability densities does have a decomposition structure. But I don't know the functions ui and vi's. So ui and vi's are basically, I would say, the principal functions of the unknown transition densities. Okay. And now also to make things computable, I also need to have a pre-given Hilbert space. So I know that I can already have something to embed the basis of the feature of the state features. So now the question is, I want to estimate the features. Actually, I call it state embedding. So I want to find the function psi, which maps a state x into a vector. And hopefully, I want the span of the psi function to be approximately equal to the span of the unknown u functions. Okay, so if that is true, then psi should be good features to use. Does it make sense? Okay. So now if we think about this problem, I want to basically estimate the leading singular space of a large matrix or a large set of conditional densities. So really, we are trying to do spectral estimation. So this is actually a statistical problem. So we propose one solution. So it's actually a very simple algorithm to implement. So the input is going to be high dimensional time series. So we have the data, the time series data x1, x2 to xt. And also I want to not have a kernel space to begin with, and I have the kernel function k. Okay. So the first step is, okay, I don't want to work with non-parametric function approximation because the dimension is too high. So I want to make everything smaller in dimension. So I'm going to open up the kernel space. And how do we open up a kernel space? Ben had this very nice work on how to approximate an RKHS using random Gaussian features. So we can do that. By doing that, it's possible to approximate the RKHS using a finite dimensional space. Okay, so we start by opening up the kernel function, and then we have nice random features. Now the second step is we try to approximate the projection of the transition kernel onto the random feature space. Okay, and in this way we are actually computing a low dimensional matrix. And the third step is very simple. We just do singular value truncation. Okay, so we have a low dimensional proxy for the higher dimensional transition kernel, and then we further open it up and look for its low rank structure. Okay, so after this, essentially we have already figured out this mapping per se. So it should be a way, so it can be thought of as a mapping which is a compression of the true conditional density. Okay, and hopefully it's a smaller dimensional vector. And we proved a bunch of error bounds for this method. So one theoretical result which is worth noting is the following. So if I have two states, x and y, and we try to understand the similarity or distance between the two states. So by definition of state should be the sufficient statistics to characterize all the future probability distribution. So we characterize distance between two states using the L2 distance between the conditional transition density functions. Okay, so two states will be similar if they have similar transition distributions. Okay, so we show that the embedding method gives me a low dimensional per psi vector, such that if we look, sorry about the typo, this should be per psi y. If we look at the distance between two states in the embedding states after we are done with the computation, the distance in the embedding state is actually very close to their distance, to their actual diffusion distance. And also, this error bound depends only on the rank and some condition number and the length of trajectory. So essentially, the sample complexity could be very small, and it has nothing to do with the original dimension. Okay, and of course, we proved some error bounds for that, which I don't have to show here. Okay, so now basically we found a way to map state space into an embedding space. And in the embedding space, the distance in the embedding space characterize their distance in terms of their transition distributions. Okay, so now we can do something further. We can actually use this to identify metastable clusters. So metastable cluster is a notion in dynamical systems. It basically says that, okay, can I basically find a partition of the state space such that within each cluster, the random walk or the diffusion process is likely to stay within the cluster after an amount of time. So this is a notion which was commonly used in dimension reduction for molecular simulation and chemical dynamical process. Okay, so after we have estimated the state embedding, so the problem for finding metastable clusters actually reduces to just a k-means optimization problem, which is very simple to do. Okay, so I'll just show you one very simple example. So this is a diffusion process defined using this potential function. So it's a very simple two-dimensional diffusion process. And based on a very short trajectory, and we can actually learn metastable clusters for different, for different time horizon. So basically, for states within the same cluster, so they share very similar dynamics within the time span. Okay. And one may say that, okay, can we do something more interpretable to understand dimension reduction? I mean, features are a little bit too abstract. So another way to think about feature representation of Markov decision process is through soft state aggregation. It means that, okay, suppose that we are observing trajectories generated by a high-dimensional process, a high-dimensional random walk. But however, it's often true that the trajectory we observe generated from a simpler process down there, which is latent. And my observation and the underlying metastate are related to each other through aggregation and disaggregation distributions. So this is a very classical model from stochastic control and RL, I would say 20 years ago. Okay. So this model translates into linear algebra as a non-negative decomposition of the transition matrix. Okay, and they're equivalent. Okay, so how do we understand this in the context of features? Okay, we can think about it this way. So suppose that we are observing the trajectory generated by the random walk. And I already explained that using the trajectories, we can estimate the embedding or the feature functions. So say that we have done that. Okay, and now let's say that my embedding space or feature space is 3-dimensional. So we can look at my state space in the feature space. Now I have a scatter plot for all the states. So now what does soft aggregation and non-negative decomposition mean? It actually means that in the plot of all the states, there are a number of extreme states. And those extreme states, they actually generate a convex hull that should cover all the states. So this is nothing but a simplex structure of the state space. So we can use this structure to figure out the extreme states. And actually, we call them anchor states. So they are analogous to anchor words from topic modeling and non-negative factorization. Okay, and the anchor state hopefully should tell us something about what is really underlying the process. Okay, and again, we prove some theory, and I'm going to skip. Okay. Okay, so this is a numerical experiment which I found very interesting. So the data is just taxi trips from Manhattan. So each data point is one single transition, so one pickup location and one drop-off location. And we try to model this as a Markov trajectory, and then we use the embedding method to find the leading feature space, and then we use the simplex polytope method to find the extreme states. Okay, so it turns out that the extreme locations in the taxi example coincides perfectly with landmarks in Manhattan. Okay, so for example, like this is really the stock exchange WTC area, and upper there we have the area of the 33rd Street and Koreatown area. We also have the Museum Avenue. We also have the Times Square area. So those locations show up naturally as extreme points in the state space after embedding. Okay, so finally, we did an experiment using an Atari game, Demon Attack. So Demon Attack is like a super simple game to solve. So basically, the game is to move this cannon around and try to shoot the demons. Okay, and we have to choose a kernel, so we choose the kernel specified by DQN to reduce its dimensionality. So we use DQN, the neural network, as a kernel map, as a feature map. Okay, and then we apply state embedding for dimension reduction. So this is the states before embedding. Okay, and this is the states after embedding. So we are visualizing the distribution using t-SNE, which is basically a tool for visualization high-dimensional data in two-dimensional space, which is commonly used in biology and genomics. Okay, so first, if we look at this before embedding plot, so if you're familiar with t-SNE, so this plot doesn't look too nice. The structures are not very obvious. So at least after reduction, there should be more clusters after embedding. So that's one thing. And also, so we try to look for a pair of states that were farther apart before embedding, meaning that the states should be raw pixel images that do not look similar. That's why they have larger distance. And then we also look for states with larger distance here, but they look similar after embedding. So I just want to understand what is embedding doing here. Okay. So those are the pairs of states we identified. So we can see something interesting. So, for example, in the first pair, let's see. Okay, I don't know if you can see the purple arrow there. So the purple line, the vertical purple line is the laser, which is about to shoot the demon. So actually, in those two plots, both states are about to score. And also, this is if you look at the position for the laser and also the position for the cannon, both cannons are moving to the left. So somehow those two states are considered to be close in terms of in terms of playing the game after embedding. So they should share similar features. And in this one, so you can look at the demons there. So they look a bit like obscure because they are just showing up. They're just appearing. And so this is actually the state where new demons are appearing. Okay. And this is also interesting. This is really just idling. So there's nothing up there to shoot. And but what's I found interesting is in this case, so the cannon is actually moving from left to center. In this case, the cannon is moving from right to center. So the next state for those two states are going to be roughly similar. They are both moving to the center. Okay, so I found this to be a fun example. So basically, it's possible to identify state embedding in a way that we preserve similarity in terms of whether they share similar future paths, not only similarity in the images. And I feel similarity in sharing future paths should be actually the key to understanding what is really a state. And there's a lot more to be done here, and I feel like understanding dimension reduction together with feature implementation and also coupling them together with all the nice algorithms might lead to future breakthroughs in this area. Thank you very much. They are my collaborators.
Take a couple of questions. One or two.
So one question, I guess, regarding the spectral decomposition of the transition kernel. I guess one challenge is the non-negativity constraints and the function sum to 1. Do you have any kind of I guess, have you thought much about this, or what can go wrong with that?
So, for example, in this example, we didn't impose the assumption at all. So I would say non-negativity is actually not needed for preserving diffusion distance. Also, non-negativity is not needed for proving sum complexity and regret. So the only place where we use non-negativity is here. So this uses the idea of extreme point, which is based on non-negativity and convex combination. So I think with non-negativity, we can reveal something more interesting about the underlying structures. But probably if we only care about dimension reduction, maybe we don't need non-negativity. I think this is an open problem. Non-negative factorization is definitely much harder than just factorization. That's a very good question.
Any other questions? Okay, let's thank Mengdi again.